All right, so what we're going to do today is we're going to start on the second textbook, the one on calculus. As you see, we only have three classes left, so obviously we can't cover a lot on calculus. The book is very thick. Most of the topics will be covered in the second course in the series, Econ 1111. So in that course, there will be no linear algebra. It's just purely on calculus. Right, so we cover just the basics, the first few chapters of the calculus, and the rest will be left to the next term. And to talk about calculus, the usual departure point is limit. So today we're going to talk about limit. What is limit and what do you do with it? The first part is to understand what limit is about, and that's in chapter 1.3 to 1.5 in our calculus textbook. This textbook is a very long-standing textbook. Like when I studied calculus in university, I used this textbook. So you should be able to quite easily find an old version of this textbook. The content is pretty much the same. Like calculus, right? It goes back to Newton. So how much change could there be? So you could totally use an old version if you need to. So motivation. Why would we need to learn the topic of calculus? Actually, specifically, why do we need to learn differentiation? In many economic studies, we want to find the rate of change of function. Pretty much any mathematical theory you would see as an undergraduate economics major would involve differentiation, because all the theories involve finding the rate of change. What rate of change do we need in economics? In the most basic level, we need marginal utility, which is the rate of change in utility. How fast is your utility changing based on how much stuff you're consuming? So utility, for those who are not econ majors, utility is a number. Higher means better. You like it more. So now you can imagine most of the time we would assume that when you have more things, you are more happy, right? You have one iPhone makes you happy, two iPhone makes you happier. So more things usually make you happier. And in economics, you represent that by a higher utility value. What we want to know very often is how fast is your utility going up? Is it going up? Is it going down? How fast is it going up? So that's the rate of change in utility, and that's called marginal utility. That's consumer behavior. In production and firm behavior, you want to know how fast is revenue going up as you produce more. Now this might very well not be positive, right? You can imagine if you produce a lot of your products, you might actually get less in revenue if you have to put your products on sale. Things are expensive when they're rare. There's a point where you're producing too much and you're flooding the market, and that would reduce your revenue instead of increasing it. So that's the rate of change in revenue. How fast is your revenue going up as you increase output? So that's half of the equation in terms of making money. How much money you're bringing in. What's the other half? Well, the other half is how much money you're paying out. That's the marginal cost, the rate of change in cost. As you produce more, things get expensive. Right? Why couldn't Apple produce even more iPhones when so many people want it? Well, part of the reason is it's simply prohibitively expensive to do that. Apple is pretty much exhausting all available capacity when it prepares for a launch of an iPhone. It can't produce more. There's simply no capacity. Well, if Apple really has to produce more, they might need to build whole new factories. They need to find new contractors, and it might be prohibitively expensive to do so. So that's the other half of the equation. In order to make money, you have to think about how much money you are bringing in and how much money you are putting out. The rate of change of these two are going to determine how much, whether you're making money or not in producing a particular unit of output. So in economic theory, you have rate of change everywhere. Pretty much all theories depend on rate of change, and in turn, differentiation helps you to find rate of change. So that's why we need to learn differentiation. To understand the idea, to understand how we find rate of change, we can use a graphical representation of a function, which would be typically a curve. In economics, once you go past demand and supply, you find that you rarely would be dealing with straight lines anymore. Most of the time, you'll be dealing with curves, like this. Straight lines are not very realistic in many cases. For example, if your revenue is a straight line that goes up, what that says is the money you get is always proportional to the quantity you sell, which is not very realistic assumption, because if you're trying to sell many units, eventually people would not be willing to pay a high price, right? Things are expensive when they're rare. So it seems unrealistic to assume that you have a straight line relationship between revenue and output. Similarly, it's not realistic to assume that utility is a straight line relative to how much iPhones you have. You might be you're probably very happy with your first iPhone, but then you don't really need a second iPhone, and you certainly don't need a third iPhone unless you're driving taxi. Then you might want like a whole rows of phones for your business. But for a typical person in Hong Kong, there's no reason why you want multiple iPhones. So you might be happier with multiple iPhones, but certainly you would imagine that the first iPhone makes you a lot happier than the second and the third. Once again, that means that utility does not have a straight line relationship with the quantity of the product you have. So in economics, typically you're dealing with a curve. How do you find the slope of a curve at a particular point? Let's imagine we're trying to find the slope of this particular point, this red point here. And what can we do based on just high school mathematical knowledge without calculus at all? Without calculus, what you can do is, well, first, one way is you can imagine that, well, the slope it's really denoted by a red line called a tangent line. This line shows you what the slope should be, right? You can do that. The problem is, it's easy to draw this graphically, right? But how do you actually get the slope if I give you a function? Are you supposed to draw the diagram and try to figure out this red line? How do you go from a function to a slope? If I give you a function fx, how do you find the slope? Based on high school mathematics, the way you do it is to use the two-point formula. That's something that everyone learns. Use two-point formula to find the slope. To use the two-point formula, you have to pick a second point, right? So that's because the way that the two-point formula works is y2 minus y1 divided by x2 minus x1. That's how the two-point formula works. So you have to pick a second point. What point should you pick? Well, let's try picking a point that is a bit far away. The green point at the bottom left corner of the diagram. With the second point, then you can use the two-point formula, right? Y2, you can have, so y2 minus y1, x2 minus x1, and you can represent the slope from two-point formula by a line joining the 2 points. So this green line in the joining the 2 points represent the slope you get from 2-point formula. If you look at this green line, it's quite clear that it's a pretty bad approximation to the actual slope. The actual slope, if you draw it graphically, is this red tangent line. But the green line clearly has a very different slope. So the 2-point formula is not giving us an accurate answer. And that's understandable because the 2-point formula is only accurate if you are trying to find the slope of a straight line. And we're trying to find the slope of a curve here. So it's an approximation at best, and it's a pretty poor approximation at this point. So what do we do? If you only know high school mathematics, and remember before Newton, everyone only knew high school mathematics, right? There was no calculus before Newton. So what do? Well, you can try to improve your approximation. The approximation gets better if you pick a point that is closer to the point you're trying to find the slope for. So you can see as you pick a green point that is closer and closer to the red point, the approximate slope, these green lines, gets closer and closer to the red line. Right? So the 2-point formula gives you a better approximation if the second point is closer to the first point. You can see that by the 4th point is pretty good. Not yet there, but it's pretty good, pretty close. So what would be the most accurate approximation you can get? Well, you want to pick the second point as close to the first point as possible, because clearly as they get closer, the approximation improves. So you want to pick the second point that is as close as possible. And where do you find the closest point? The closest point would be that point, right? The closest point to the point you're interested in is the point you're interested in. So it seems like, based on our logic, if you can pick the second point equal to the first point, then you would get a completely accurate approximation. That's a good idea, except you can't use the 2-point formula if the 2 points are actually identical, right? If the way the 2-point formula works is y2 minus y1 and x2 over x2 minus x1. If the 2 points are identical, then you have 0 divided by 0, which is not 0. 0 divided by 0 is undefined. Any number divided by 0 is undefined. Right? So it doesn't work. So now what? Well, here is where the concept of limit comes to rescue. Even though 0 divided by 0 is undefined, it turns out we can get a pretty good idea of what the slope is going to be based on very, very close approximations. As you'll see later on, the approximation actually has a pattern. So based on the pattern, you can deduce what the accurate slope is supposed to be, even though you can't actually calculate it with the 2-point formula at that point. So that's what we're going to do with limit. So first, an intuitive definition of limit. This is not a rigorous mathematical definition of limit, but it's an intuitive definition. So if you can make a function arbitrarily close to a value L, so L is just a symbol, right? So just a value. If you can make a function arbitrarily close to a value by restricting x to be sufficiently close to another value, then we say that the limit of the function as x approach a equals L. Right? So this is the mathematical notation, and this is how you say it in English. If the function f, if you can make the function f arbitrarily close to a value O by restricting x to be sufficiently close to a value A, then we say the limit of f as x approach A equals O. So that's the definition. If this is the first time you see the definition, it's probably hard to understand what it really means. So it's probably easier to see a diagram. Well, let's take a look at a diagram and see and try to figure out what this definition means. And here's a diagram. So I've drawn a function that goes up and down, up and down, up and down. And let's imagine at a certain point A, right, the function takes on a value O. Yep. So now if you look at a point that is very far away from A, like x1 here, it's very far away. There is no guarantee that the function would take on a value that is close to O, right? After all, you're very far away. Sometimes it could, if you have a horizontal line, then yeah, it would take on exactly the same value as in A, right? Because it is like if you have a straight line, then yeah, like any point you pick would have the same value. But other than that, in a typical line or curve, when the x value is very far apart, there's no guarantee that the function will take on values that are very close by. So in this case, you can see that fx1 is very close from L because x1 is nowhere close to A. What if you pick what if you pick another point that is closer to A? x2. x2 is very close to A, and as a result, the function also takes on a value very close to L. So that sounds intuitively right? That should be the case. As you move closer to A, you would imagine that the function should also take on a value closer to L. If you're far away, it could move up and down, right? F could go up, down, up, down, up, down. But at some point, as you get close enough to A, the function should take on a value close to L, as you can see in this diagram, right? It's just a matter of how close you need to be. Right? If your function is going up and down a lot, you would need to get really, really close. If your function is relatively flat, like this, right, then you might not need to get very close because the curve is kind of flat. The idea is as long as you get close enough, the function should take on a value very close to L, right? No matter how wiggering the function is. So that's the concept of limit. Get close enough to A, and the function would take on a value close to L. That's the idea of limit. Now here's a case where the limit does not exist. You can see this function is a kind of like a step function. is a step function where you have a vertical break at A. You have a vertical break at A. And if you think about what happens, the idea of limit is, well, the function, what value is the function moving towards? If you look at the function from the left-hand side, as you get closer to A, the function gets closer and closer to the value L1, which is okay. That's just like what we have seen in the previous slide. As you get closer to the point A, the function gets closer to a particular value. Now the problem is, if you look from the other side, from the right-hand side, as you move closer to A, the function also moves closer to a value, but it's a different value, L2. So for this particular function, as you get closer to A, the function gets close to not one but two values, depending on which side you're looking from. If you look from the left-hand side, the function gets closer and closer to L1. If you look from the right-hand side, the function gets closer and closer to L2. So the function gets close to two values, depending on which direction you're looking from. In terms of notation, this is how you write the notation. So you can see the limit of when x approaches A negative, fx equals to L1. Now, what do we call this? We call this the left-hand limit. This is the left-hand limit. The left-hand limit, this A superscript negative means that you're approaching A from the side at which it's smaller than A. Right? So it's A negative, because you're approaching A from the direction where the numbers are smaller than A. So as x approach A from the left-hand side, that's usually how you say it. As x approach A from the left-hand side, fx approach 1, as you can see from this diagram here. The other side is called the right-hand limit. It's coming from the right-hand side. As x approach A from the right-hand side, so it's A plus because the numbers are bigger than A. As x approach A from the right-hand side, the function approach the value L2. And L1, L2 are different numbers. So what you have here is that the function is clearly not moving towards a value. It's moving towards two values, depending on which direction you're looking at. By the definition of limit, a limit only exists. Now this is not a typo. This is IFF is the mathematical notation for if and only if, right? If and only if. The limit only exists if and only if the left-hand limit equals the right-hand limit, which is to say, the limit only exists if the function is approaching a particular value, a value, from both sides, right? It must be approaching a value from both sides. It cannot be approaching one value on one side and another value on the other side. It must approach a single value from both sides for a limit to exist. Right? So whenever you have a function that looks like a step function, the limit would not exist. It's important to note that the limit does not exist at A. A limit the existence of limit is relative to a particular point. So the limit does exist, for example, at this point here, because in this point you can see that the function is moving towards the same value on both sides. So limit, the existence of limit is not relative to the function, it's relative to the point. For this function, limit does not exist at a because the function is moving towards two values. But at any other point on this function, the limit does exist because you can see that the function does move towards a single value at any other points other than a. So limit existence is relative to a point you pick on a point on x. Right, so limit existence, it's relative to a point, and it's asking whether the function is moving towards one value or two values. If it's moving towards two values, then the limit does not exist. All right, so does that mean that the function has to be joined together in order for that to work, right? Because clearly, so we just said that when you have a step function, then the limit does not exist at that point. So does that mean that you need the function to be completely joined? Let's take a look at this example. So this example is a very weird example. It's a very weird example. It equals to, so the function equals to x for all values of x except if x equals to a. If x equals to a, the function takes on the value x plus 1. So I've plotted this on the diagram. So you can see that it's a 45-degree line except at the point A where it takes on a plus 1 value. So you have this particular point that is popping up. Does the limit exist? Does the limit exist? Remember, the idea of limit is the function approaching a single value from both directions. So is it? You can draw. From the left-hand side, if you look at it, it's quite clear that the function is approaching a, right? It's approaching a value of a. In notation, you write limit a approach a negative fx equals to a, right? It doesn't matter that the fact that the function is actually taking on a plus 1 at a. What limit is about is what the function is approaching, right? And if you look at the diagram, it's approaching a. It's not approaching a plus 1, right? It's approaching a because the line is clearly passing through a, not a plus 1. So it's approaching a. Similarly, if you look at the right-hand side, the function is very clearly decreasing and approaching a. It's not approaching a plus 1. It's approaching a. And in notation, we write limit x approach a plus fx equals to a. By the definition of limit, since the left-hand limit equals to the right-hand limit, limit exists. And, well, it equals to A. So this is a weird case, but you should understand the logic if you look at the diagram. This function, you can imagine that you can just hide. Imagine that you hide what happens at A, like with a piece of paper, right? You hide what happens at A with a piece of paper, and you just look at what happens around A, and you're trying to figure out what happens to the function. Your logical conclusion would be the function will take on the value of A, because if all you see, let me just try to do that, right? Like, let's say if you hide what happens around A, right, like this. If you hide what happens with what happens around A, so you don't know what's happened. That's kind of what we're trying to do, because we don't know what's happened when you have the 0 divided by 0, right? So we're trying to figure out what's happening at that point without knowing what's actually at that point. So like this, we don't know what's exactly happening at that point. So you're trying to guess what's happening at that point from the trend, from the points around it. And if you look at this diagram now, I think everyone would conclude that the trend is x would take on the value of A. And that's the limit, the trend. Even though if we actually have the definition of the function, we know that at that point it's not actually taking on that value. But the trend is that it is taking on that value. So limit is all about the trend. Right? So the trend is that point is taking that at that point you would expect the function to take on the value of A. Now here's another case where the actual value of the function does not exist. Namely, if A takes on a value of infinity at a particular point. Infinity is not a number that you can write down, right? Infinity is bigger than any number. So what you have here is a function that gets arbitrarily big as you get close to A. As you get closer, it goes up, 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 up. It just keeps going. It just keeps going up, right? It just keeps going up. It just keeps going up, bigger and bigger. When that happens, we say that the limit of the function f as x approach A equals infinity. We have a specific name for such a point. We call that a vertical asymptote. It's just a name. Right? It's just a name. It's called vertical asymptote. And it appears in some common functions that you would see, like tangent. If you have a tangent line, if you look at the tangent function, how does a tangent function look like? Tangent function looks like this. This is how tangent looks like. And it goes up to infinity, then comes back from negative infinity, goes back up to infinity, comes back from negative infinity, and so on. So that's how the tangent curve looks like. Negative infinity. It's just so we have a very similar definition, right? If the function just gets arbitrarily negative. If the function gets arbitrarily negative large as you get close to A, then we say that the limit of the function as x approach A is negative infinity. And we also call that point a vertical asymptote. So once again, what you have here is you can't actually compute this point. Because any finite number add together would be a finite number, right? any finite number multiplied together would be finite numbers. So you don't calculate infinity, right? But we do know that it's going to be infinity. It's going to be arbitrarily large or arbitrarily negative, and we guess that we would correctly conclude that the trend tells us that the function is approaching infinity, even though you can't actually compute infinity. So how does this help us? How does limit help us with finding the slope? Well, so I'm going to first use the straight line, which does not require approximation, but a straight line is good because it's easy to calculate the values. So let's say we try to approximate the slope of the straight line with a second point. The approximation is going to be accurate because it's a straight line, but the process is the same. So let's just imagine we're trying to approximate the slope. And so we have a point X, we have a point A, right? That's the point we want to find the slope for. And we approximate the slope by picking a point very far away. Okay. What would the slope be? What would the slope be? For concrete, let's just imagine fx equals to x, right? Okay, that makes it easier to think about it. And if that's the case, right? When you pick a point x1, then the slope you find would be y1, fx1 minus fa over x1 minus a, which is x minus 1, x1 minus a, x1 minus a, which is 1, right? So that's clearly the case. Okay, so according to our approximation, the slope is 1 if you pick x1. Let's pick a point closer, x2. Let's pick a point closer, x2. Right. Once again, so slope. What is the slope? The slope would be fx2 minus fa divided by x2 minus a, which is x2 minus a divided by x2 minus a, which is 1. So the approximation says that the slope is, once again, 1. Okay, imagine you do this for a lot of points, right? If you do this a lot of points, you would still see that they all give you approximation. They give you approximation of 1. So you have a straight line. You have a horizontal line. Sorry, not here. Sorry. Okay. What we need is we want to find the slope at A, but the two-point formula does not work. The two-point formula does not work if you pick the second point being A. Right? The two-point formula only works if the second point is different from A. However, if you look at the diagram of the approximated slope, it should be clear that well, I think I no longer need to use two colors. Let's just use one color. It should be clear that the curve of the approximated slope, the function of the approximated slope, approach a particular value, right? Because no matter what other points you use to calculate the approximated slope, it's always going to be 1. So if you look at this function that represents the approximated slope, the reasonable conclusion is the function is approaching 1 at A, even though you can't calculate that with two-point formula. But the limit gives us a reasonable deduction of what the slope should be. We can't use the two-point formula, but based on the function that represents the slope, that represents the two-point formula, it's reasonable to say the function is moving towards 1. And we know this is correct. In the case of a straight line, it's quite clear that the slope should be 1 in this point. So this is actually a correct deduction. Now here's the point where the insight comes in. This is actually the definition of the derivative. This is the definition of derivative, the limit of the two-point formula. The derivative helps us to find slope because the derivative is the limit of the two-point formula. Right. So you might say, well, this is clearly unnecessary for a straight line. That's correct. What if you have a curve? Right? What if you have a curve? Now, for our purpose, let's just assume this is a log function. Right? For our purpose, we're gonna use a log function. Log function is one of the most common functions you will see in economics. So it's a very good choice for our purpose. It's something you're going to see a lot. If you have a log function, and let's say you want to find the slope at log 2. How do you do that without knowing calculus? How do you find the slope of log 2 without calculus? So right now, we just have limit, right? So what can you do? You can approximate. So let's do that. So we're going to approximate the slope. Right? We can approximate the slope by picking a point, let's say 1. Right? Let's just start with 1. So what would the slope be in this case? Two-point formula, F1 minus F2 over 1 minus 2. And for log, you do have to punch the calculator. You can't do it by hand, right? So let's do that. Log 1 is 0, no need for calculator. Log 2 is 0.69. So 1 minus 2, so that's 0.69. All right, so our first approximation of the slope is 0.69. Let's just say this is 0.5. So this is 0.25, 0.75. So 0.69 would be somewhere around right here. somewhere around here. Okay. That's, as we all know, that's not a very good approximation because we pick a point very far away. So let's pick somewhere close at 1.5. Now, clearly, this is a much better approximation. So let's do that. Slope. F 1.5 minus F 2 over 1.5 minus 2. So once again, punch the calculator. We have log 1.5. So log 1.5, that's 0.41 minus 0.69 over 1.5 minus 2. I'm going to use the calculator for this one, right? So the numbers are going to be slightly different. Okay, divided by 0.5 negative. Right, so this is 0.58. Okay, so our second approximation with the second point 1.5 is 0.58, which is somewhere around here, right? Let's pick in one more point. Let's try something like let's try something like well, do you want to, let's see how many points do we want. Let's do actually two more points. Let's do 1.9 and also do 2.1. Okay? So these points are very close now. So 1.9 and 2.1. So we now pick 2 points that are very close. So let's first do 1.9. Okay, so you can very quickly punch the calculator. So I'm just going to speed things up, right? You get the idea. So 1.9 minus f2 over 1.9 minus 2. And if you punch the calculator, that's going to be log 1.9 minus log 2. And what you get is 0.51. Okay? So now we are 1.9 and we have 0.51. Okay, finally, one more. F2.1 minus F2 over 2.1 minus 2. And once again, punch the calculator. Log 2.1 minus log 2. And divide by 2.1 minus 2, that's 0.48, right? So that's the last number we have, and it's somewhere around here. Okay, let's join the points with a line. So this line represents the approximated slope. And once again, I think it's reasonable to conclude that while we can't use the two-point formula to find the approximated slope at exactly 2, we can deduce that the slope is going to take on a particular value. What's the value? You can see that at 1.9, if you use 1.9 to approximate the slope, you have the approximated slope as 0.51. If you use 2.1, you get the approximated slope of 0.48. So what would be a reasonable guess in this case? It has to be higher than 0.48. It has to be below 0.51. A reasonable guess would be 0.5, right? So a reasonable guess would be the slope is somewhere around, the slope would be 0.5. Right? And that's, in fact, the slope of log 2. Okay. The slope of log 2 is half, 0.5. Okay. So the approximation is correct. Our guess is correct. The trend does tell us the correct slope. Right. Trend. Oh, 0.5, let's just say 0.5. Right. The trend would suggest that the slope of log 2 is 0.5, and it is actually correct. Okay. Now, what we did here is a numerical derivation of the approximation. We try many, many points. This is not something you want to do very often. It takes too much time. So what differentiation does, what the topic of differentiation does, is to teach us rules that we can apply directly. However, this process is actually very useful. It's not just, at this point, we're just using it to illustrate why the concept works. But in practice, very often, what we did here is a numerical approximation of slope. It's very important in practice because when in practical science applications, very often you do not have an analytical function for what you're trying to study. For example, how do I get a function of people's utility? You don't. The simple answer is you don't, because you don't observe what's going on in people's head. The best you have is a bunch of data. Right? And that's the case in many science applications. You simply do not have an analytical function. You have a bunch of data. How do you find the slope when you just have a bunch of data? Well, that would involve numerical approximation. Or similarly, another case would be not every function is easy to differentiate, even after we learn the rules of differentiation. Some functions are simply too difficult. What do? Numerical approximation. This method is surprisingly useful when you deal with functions that are too hard to differentiate. Obviously, we're not going to do it by hand. You could ask a computer to do it. Computer can do these kind of approximations very well because the math is very simple. It's just two-point formula. 2 subtraction, 1 division. Very easy for computers. The computer can do thousands of these in a split second. So it can give you very accurate approximation with this method. So in modern computing, this is something that's being used very, very often. But for us, as an undergraduate learning calculus, limit is like demultiplication. It's like addition to when it's like learning. It's like addition. Like when you first learn the multiplication table when you are in elementary school, like a primary school, you probably use addition to verify that the table actually works. When your teacher first taught you, right, 2 times 3 is 6, you would think, why would that be true, right? 1, 2, 3 plus 4, 5, 6. Yes, so 3 plus 3 is 6 because you can verify it with addition, right? Why is 3 times 3 9? 1, 2, 3, 1, 2, 3, 1, 2, 3. That's 9. So when you first learn multiplication table, you probably use addition to verify that it's correct. But once you are familiar with the multiplication table, you no longer do that anymore, right? Once you have memorized the multiplication table and you're convinced that it works, you no longer verify that the multiplication table works every time. So it's similar with limit. The relationship between differentiation and limit has a similar property, has a similar tone, because we need limit to get the derivative. As I just told you, the derivative which gives us the slope of a function at a particular point is the limit of the two-point formula by definition. In some sense, you can imagine that's what Newton was trying to do, right? Newton was trying to figure out the slope of a curve. He was trying to figure out the rate of change of a function. Back before calculus, all people knew was the two-point formula. So Newton was trying to figure out, well, how do you go from two-point formula to a way that you can figure out the slope of a function at any point you need? Limit. So limit of the two-point formula. So you need limit to derive the the derivative. But once you have learned the derivative and all the rules of differentiation, then you no longer use limit. Right? Once you are convinced that this is correct, then just like you no longer go back to addition, you would not use limit to approximate slope. You would directly use the rules of differentiation. So that's why we need to learn limit. This is a very, very positive way of saying you're pretty much not going to see limit again beyond this course. Because beyond this course, everything you see will simply apply the rules of differentiations. You do not need to use limit. It's all we teach limit because we need to understand why it works.